Hey, welcome back everybody. Glad you all are here today. And today what we're going to do is we're going to take a look at electron configurations and orbital notations and how that connects to quantum mechanics. So some deep, heady stuff, but if we have our periodic tables and our notes, we're going to put all this stuff together. We're going to do some practice here. Now, the sizes and shapes of atomic orbitals. The last time we got together, I had some models up here of the atomic orbitals. And if you remember, that s orbital was spherical shaped, and those p orbitals kind of had a barbell shaped, and the d orbitals kind of were teardrop shaped. There are different shapes to these. Now, there's mathematical equations that describe these shapes. That is the highest probability of where we would find these electrons. And these are Schrodinger's equations. And you may have noticed they look nothing like a planet going around the sun, which is a little weird. And you're like, wait a minute, where did that come from? That was the Bohr model of the atom, B-O-H-R, not B-O-R-E, model of the atom. This now we're going to take a look at quantum mechanics. Now the quantum mechanics is going to tell us the shapes of these orbitals and the energies of these orbitals. Is going to give us all kinds of information about these atomic orbitals. Now, this is based off of something called the Aufbau principle. And Aufbau is German, and you're like, man, we don't have enough German in chemistry. Well, here you go. Here's some German. Aufbau means building up. So when we're adding these electrons, these electron configurations, we're going to add one electron at a time, and we're going to build up these atoms. We're going to build these atoms. This is called Aufbau. So we're going to build up these atoms, and we're going to end up with something called an electron configuration. And this electron configuration is going to show us where these electrons are in our atom. And so it's Aufbau, it's building up, it's electron configuration. So here's how it's going to work for us. Now, if we imagine on our periodic table, we have elements in these boxes. And each one of these elements or each one of these boxes has an electron. So, for example, hydrogen, which would be here on our periodic table, hydrogen has how many protons? You can use a finger, not the middle finger. It has one electron, because it has one proton, neutral atom has one electron. Okay, so there'd be one electron here. And if we had helium, helium is over here. Helium has an atomic number of 2. How many electrons would helium have? 2. Now, to build up, we would have one here, and then we would have one here for a total of 2. Okay. Now, how do we do this? So, an electron configuration. Electron configuration. Now, with the electron configuration, we're going to be doing some notation here. And how this works is we might say something like this. We're going to start out with hydrogen, and we're going to build our way up. So hydrogen would look like this. Here's hydrogen, and the electron configuration for hydrogen. So hydrogen is right here, and we'd have one electron there. So I'm just going to go one electron like that. There's my electron. Now, what energy level is that? N is equal to 1. Thank you for using that finger. I appreciate that. That helps my self-esteem here. Okay, so N is equal to 1. That's the first energy level, right? And then it goes 2, 3, 4, 5, 6, 7, it just keeps going. Okay, so N is equal to 1. So our first value here, the first part of our electron configuration for hydrogen would be to put our value of N. Okay, so I'm going to say here, this is N. That's our value of N, right? And now the next thing is this spot right here on our periodic table, our orbital has a letter designated to it. That letter tells us its shape. Do you remember what letter these first two columns are? S. Okay, so This here would be the shape of the orbital here. It is an S, okay? It's an S orbital. So I'm just going to go here, shape of the orbital is an S. It's an S orbital. And then we're going to look at how many electrons there are in that S orbital. That S orbital can hold 2 electrons, but right now we only have 1 there. So we're going to call this superscript 1. Okay, so that's the number of electrons in that shape orbital. Okay, so in that orbital, number of electron in, what do we call that? Help me out here. Hey, Michael, Grant, Jack. This superscript here, that's the number of electrons in the, what do we call that, a subshell? Does that sound right? Okay, I'm going to say in subshell. Thank you. I know this doesn't help your confidence in me, but I struggle with math and stuff, and it gets worse when people are looking at me. So we could play a game. I'm really smart if you don't look at me. I'm also invisible. Yeah, close your eyes. Right? Open them. Okay. All right, so this is hydrogen. Now, if we wanted to do helium, according to the Aufbau principle, we're going to build up. So helium is going to be over here, and this box right now, I know it's over here on the right-hand side, but it would actually be over here. So I'm just going to go like this. I'm just going to go boop, 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 like that, okay? So it's really over there, but it's not. And I'm going to put an electron there. Do I go like this? No, I don't do that. That's a no-no. Because the spins, they have to have opposite spins. That's the 4th quantum number. Excellent, nicely done. They have to have opposite spins. Okay, so my value for n is 1. My orbital shape is S. Okay, nicely done. And then my number of electrons in that orbital is 2. Oh, man, you guys are rock stars. Okay, let's do a hard one. I think you're thinking, let's do a hard one. Let's do a, well, okay, what do we have here? No, let's do a hard one. Okay, let's do a tricky one. Let's do neon. Let's do neon. Neon. Okay, so now neon is going to be over here. Here's neon. And so I'm going to have an electron here, electron here, electron here, electron here, electron here. What? Oh, that's nitrogen. Yeah, that's what I said. Nitrogen. Let's do nitrogen. Who's writing in pen? Shame on you. I think you'd learn by now. Okay. Yeah, we're doing neon. I'm sorry. Nitrogen. Just wait till I screw up potassium and phosphorus. Yeah. Oh, yeah. Oh, yeah. Okay. Nitrogen. Okay, so here's nitrogen. Now we're going to build our way up. So we're going to start with n is equal to 1. Okay, so we're going to take these first 2 electrons in the first energy level. N is equal to 1. And so we're going to go 1s2. All right, there's 2 of them there. And then that's this whole energy level. And now we're going to go to the next period here. We're at the 2nd energy level. This is going to be 2s2. All right, so that gets me to here. And now I want to get over to here. Okay, so that's going to be 2p. Oh, nice. Oh, you folks are amazing. Yeah, because this is the p orbital here. Okay, nice. So that's p. What? Did I miss something? Okay. All right, so there's the p orbital. Did I miss one? I don't know. do I have, let's see, it should go 1, 2, 3, 4, 5. You're right, there's, there we go. Right? 1, 2, 3, 4, 5, 6. Yeah, that totally works. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, here we go. This would be the d orbital. Okay. Yeah, oh man, okay, fine. It's a good thing I didn't go to art school. Hey, you know who didn't make it through art school? Hitler. Okay. Sometimes you should just shut up, right? Okay. So 2p3, there's 3 electrons there. Okay, so it's 2p3. Nicely done. Now, this is our Aufbau principle. This is building up. And as we go along, we just keep adding and building up our electrons. Okay? And then, now, let's see, we have something here called the effective nuclear charge. Okay, the effective nuclear charge. This tells us that there's a positive charge on the nucleus, which makes sense because it has protons in it, right? Protons have a positive charge. And these protons pull on the electrons. They pull the electrons in, okay? But these electrons shield other electrons on the atom. And this gets a little confusing. So it's like this. If we have an atom and we have, I'm going to go like this. Here's my protons have a positive charge. Here's neutrons have a neutral charge. This is my nucleus. This has a positive charge. And then I've got electrons out here. Now these electrons going around like this have an attraction to the nucleus. They're attracted to the nucleus. Now as we add more shells like this, so this is n is equal to 1. I'll just go n is equal to 1. And then the next level here, we have n is equal to 2. Okay, we're getting further away from the nucleus like this. These electrons are also attracted to the nucleus, but these ones here are shielding because they have a negative charge. Okay, so negative charges repel each other. And so the attraction this electron feels for the nucleus, we call this the effective nuclear charge. And as we add more and more layers, there's more and more shielding that happens, that gets in the way of these electrons. There's still an attraction, but there's shielding happening, and this happens with electrons. And what we're going to find then is this is going to affect the radius or the size of our atoms as we move across a horizontal row. Okay, so that's coming up. Now, as we keep adding these electrons, we're going to have core electrons and we're going to have valence electrons. Now, our core electrons, these are the ones that are not involved in chemical reactions. So as we take a look at our electron configuration here, we can see we have 2 different energy levels. Here's the first energy level, here's the second energy level. Now, these electrons here, these ones are in the outermost energy level. And so we would call those our valence electrons. So outermost energy level, I'm going to call these ones here my valence electrons. They are in the outermost energy level. How do I know? Because the energy level here it's the highest number of n. And then these electrons here, these are my core electrons. Core electrons. They're not involved in chemical reactions. So later on we're going to find out that these electrons will be gained or lost. Okay, these ones in the valence shell will be gained or lost. These ones won't. Those ones in the core electrons will not be gained or lost. And then we're going to have something called degenerate orbitals. And degenerate orbitals, these are orbitals with the same energy. So for example, here this is n is equal to 4. N is equal to 4. But here we have d. And this d orbital here, this is actually in the 3rd energy level. And so we might refer to this as a degenerate orbital because even though it's here with 4, it's actually the same level as n is equal to 3. It's a degenerate orbital. Okay, just fancy terms. Just some fancy terms. Okay, now that's electron configurations. Now we're going to do something called orbital notation. Now orbital notation is the same thing here, except we're just going to draw some boxes and throw arrows in boxes. Not like we've never seen that before, right? We've done this. We've drawn boxes and we've done arrows. So now we're just going to combine these two and make some boxes. So let's just start out. We'll start out with a simple one. We'll do hydrogen here. Let's do hydrogen. Okay, so hydrogen, like this. Here's my electron configuration. It's 1s1. Now if I'm going to do my orbital notation, let's say I'm going to go orbital, orbital notation. Okay, so for my orbital notation, okay, I'm going to go 1s1, okay. I'm going to draw a box for my orbital notation. Here's my box, like this. Here's my box. And that box would be this box here, which has 2 electrons in it. This is a subshell. And so I'm going to put my 1 electron in there, like this, okay? And that is my orbital notation, that box here, 1s1 with that 1 electron. Now if I do helium, now helium, this is going to be 1s2, right? 1s2. So I'm going to draw my box. It's still just one box because it's combining the 2 boxes here for my suborbital. And I'm going to put my 2 electrons in there, and they will have opposite spins. So there's my orbital notation for helium. And you're like, okay, I got this. It's not so bad. Gets a little tricky now. We're going to now take a look at neon. Now with neon, nitrogen, I said that. Oh, man, I should just move on, just move on, just move on, like nothing happened. Okay, so nitrogen here, nitrogen is 1s2, 2s2, 2p3. Okay, so now I'm going to have to draw some boxes. Now my first box is going to be for this s orbital. So I'll put a box here, like this. Here's my box. Okay, and then I'm going to do another box here for my 2s orbital. Another box here like this. And then my 2p. Now, how many boxes do I do? I have 1, 2, 3 suborbitals. So I'm going to have 3 boxes here, like this, okay? Like that. And this right here is my 2p. This is the p orbital here. Okay. Now my electrons, I have 2 in this s orbital, 1, 2. 2 in this s orbital, 1, 2. And then I have 3 in this p orbital. Now this is where it gets tricky. And say, well, don't draw this if you're drawing in pen. I could go 1, 2, 3. That's an option, right? Or maybe I could go like this. Or I could go like this. How do I do it? There's different options here. And one is better than the other. And so how do we do this? Now we have a rule for this. This is called Hund's rule, another famous dead guy. Hund's rule tells us that the lowest energy electron configuration for degenerate orbitals is the one with the maximum number of unpaired valence electrons within this, with the same spin. Okay, so what does that mean? Blah, 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 blah. What it means is we just go left to right and we just add 1 electron at a time. So we go 1, 2, 3, okay? So that each of these boxes only has 1 electron. They all have the same spin. And then if we had a 4th electron, it would go here, and then the 5th one would go here, and the 6th one would go there. Okay? That's Hund's rule. In your textbook, there's a whole bunch of these where it shows the electron configurations. The electron configurations shows you the orbital diagrams. And then there's this over here, the condensed version. Because at some point, when we start getting into elements down here, then your electron configurations get really long. And it's a lot easier if you can just take your core electrons and substitute in a noble gas. So, for example, let's take a look at this element let's do this one here. Let's do that one there. That's scandium, Sc. You see that there? Scandium. Okay, so if I want to do the electron configuration for scandium, that would be a lot, right? But I can make this shorter. So I'm going to go like this. I'm going to say scandium. I'm just trying to find space here. Okay, Sc, scandium. Okay, and I'm going to put this right here, Sc, just so we remember where that is. I'm going to use the Nobel gas just before it, which is here. So that's the 3rd energy level. That's argon. Is that right? Okay. All right. You know, there used to be really good chemistry jokes, but all the good ones, argon. Yeah. You know what you do with the dead chemist? Bury him. Yeah. I'm here all week. Okay. All right, so scandium, we're going to go is argon, okay? Argon, so those are our core electrons, and then we're going to do our valence electrons, which brings us here, so that's 4s, 4s2, that would bring us here, and then we have 1 electron here, that's going to be in our d orbital, and it's not 4d, it's 3d, 3d1. 3d1. So that would be this electron here. Now, that's the shorthand for it. Now, when you do the online homework and you look online, you might see these two flip-flopped because we do this in order. Notice that 1 comes before 2, right? And here we've got 4 and then down to 3. And so sometimes what people will do is they'll take this and they'll go, or it could be 3d1, 4s2, and the energy levels are in order. Okay, so you might see it this way, you might see it this way. When you do the online homework, I think you're going to have to do it this way. You're going to have to put those orbits in the correct energy order.